Hi, it's Mr. Baker here. Today we're going to be looking at angular velocity and circular motion. Okay, so we're looking at angular velocity today. We're going to look at how can we describe the speed of an object when it's travelling in a circular path. So, for example, this satellite travelling around the Earth, how can we describe how fast it's going? So to describe angular velocity, we've got to describe angular displacement. So angular displacement and angular velocity, like linear displacement and linear velocity, are vector quantities. So in other words, they've got quantities with a direction. Displacement, we can call it displacement x, is a distance with a direction. Linear velocity, v, is a speed with a direction. It's the rate of change of displacement with time. So we would say that velocity is the rate of change of displacement, delta x, the change in displacement, and delta t, the change in time. So v, velocity, would be delta x divided by delta t. Angular displacement, it would be delta theta, is the angle moved through relative to a specific axis. Angular velocity then, omega, is the rate of change of angular displacement over time. So if delta theta is the amount of angles that have been moved through, then the amount of angles that have been moved through in a certain amount of time would be the angular velocity omega. So omega equals delta theta divided by delta t. And we've just looked at in previous lesson that we can use radians to describe the amount of angles in circular motion, and so the units for omega would be the radians per second, the amount of angles moved through in radians in the amount of time in seconds. So let's see if we can come up with an equation for v. So v here, so we've got an object travelling around in a circular path. The circle that it's going around has got a radius r, and we could say that the instantaneous velocity, the velocity at which at any point it would have, would be v. So that would be going off at a tangent here in this direction. If it was over here, if it was travelling around in this direction, then if it was here, the tangent would be coming off that way. If it was down here, the tangent would be coming off like that. And that v would be the same in all of those different positions, as long as the speed around that circle is constant. So we know that the distance covered by an object moving in a circle in one period is the circumference of the circle 2 pi r. So one period, remember, is the time it would take to go around one circle. And so if it's going around 2 pi radians, then 2 pi r would be the circumference that it would travel. The radians times the radius, that would give us the circumference of the circle. We also know that speed is distance divided by time, and so our angular velocity would be the distance 2 pi r divided by the time, and in this case the time is the period, the time period, t, capital T. So we just found an equation for v, for our instantaneous velocity. Let's see if we can find an equation for omega, which would be the angular velocity. So the angle an object moving in a circle moves through in one period is going to be 2 pi radians. So in one time period, it's going to move through that many angles, 2 pi radians. All the way around a circle is 2 pi, so 2 pi radians. And so we can say that delta theta divided by delta t, so the amount of angles moved through in a certain amount of time, is going to be our angular velocity. So we're looking at how many angles we've moved through now rather than the distance. And so if we've moved through 2 pi radians in the time of one time period, then our angular velocity omega is going to be 2 pi over capital T. So with these two equations we can link them together. So we've said that our instantaneous velocity v is 2 pi r over t, and we've said that omega is 2 pi over t. So what we can do is we can put those two together, and we can find that v would be equal to r 2 pi over t. So that we've got 2 pi over t here, 2 pi over t here, and so v is just r times 2 pi over t, and if omega is 2 pi over t, then that means that we can just substitute 2 pi over t here for omega, and so we get an equation that links our instantaneous velocity v and our angular velocity omega. So v equals r omega. Really important equation linking those two together. Right, so we've got our two equations and we've linked them together. There's just one more thing that we can do. So if we say that frequency is the number of rotations per second, like that, frequency, number of rotations divided by the time it takes, then period equals the time taken for a number of rotations, we get t would be 1 over f, and likewise f equals 1 over t. So we can say that quite happily. And so because we've just said that omega is 2 pi over t, if t equals 1 over f, or f equals 1 over t, then we can say that omega equals 2 pi f as well. So we can say that omega is 2 pi over the time period t, but we can also say that omega equals 2 pi f as well. So another really important relationship. Okay, so that's the end of this one. We have described angular velocity, and we've looked at how we can describe the speed of an object when it's travelling in a circular path in a couple of different ways, and we've looked at the relationship between them as well. Okay, so that's it for today. These are the things that you should be able to do, so check that you can do those. I've been Mr. Baker, and I will see you next time. Thank you.